In this lecture, we will discuss about something known as a field. A field is a ring with some additional structure imposed on it. Okay. With additional structure imposed on it. Okay. So we'll see what are those additional structures. Okay. So a set F with the binary operators plus and product or multiplication is a field if the following properties hold. Okay, the following holds. Okay, the okay, first thing is the set has to be a ring with the operators plus and product, addition and product. Second, there is a unique additive identity E and a unique multiplicative identity 1 in the set F for all xy in the set F. The product operation or the multiplication operation is commutative. And number 4 is for every x in F and x not equal to the additive identity element. Okay, there exists a unique element which we label as x inverse in the set F such that x product with x inverse is same as x inverse product with x, which is essentially equal to the multiplicative identity, is equal to the multiplicative identity. So if you summarize what essentially it means that if you have a set along with two binary operators defined on the set such that it satisfies the closure property, then it satisfies the associativity property, it has a unique additive identity element E, it has a unique multiplicative identity element 1 represented by the double scripted 1, it satisfies the distributivity. Okay, basically all those properties that you can have for a ring. And please remember, in a ring, the addition operation that you are defining is a commutative operation. So has to be a abelian group. Okay, and in addition to these, what you need is the multiplication operation as well has to be commutative. Okay, which is a part of a ring being a commutative ring, and on top of it, similar to the existence of a inverse corresponding to the addition operation, there has to be a unique inverse of every vector, sorry, not vector, of every element in the set F, except for the additive identity. Barring the additive identity element, whatever elements are there in the set F, you should have a unique element which we are basically denoting by this x inverse symbol, such that the product of x and x inverse, or the product of x inverse and x, both of them result in that multiplicative identity element which we are representing as a double shifted one. Okay, so if you consider the examples, set of rational numbers, okay, q, with the addition and the product operation. So the multiplicative identity element is 1 and the additive identity element is 0. Also, for rational numbers, basically we know that rational numbers is a set, is a ring, okay, and the product operation is commutative. So the set of rational numbers with the addition and product operation is a commutative ring. Okay. Additionally, you have the unique identity element 1 and unique identity element corresponding to product operation is 1 and unique identity element corresponding to the addition operation which is 0. Okay. Also, barring 0, the remaining rational numbers that you have, they have a unique inverse of them, so that the product of the rational number with its inverse always results in the multiplicative identity element which is 1 in this case. Okay, the set of rational numbers is a field. Similarly, one can verify for a set of real numbers with the addition and the dot operation. Also see it for set of complex numbers denoted by C with the addition and the dot operation. What about the set of integers with the addition and the dot operation? Is this a field? We know that the set of integers is a commutative ring. There is a unique additive identity element 0 and a unique multiplicative identity element which is 1. But the question is, will there an inverse exist, multiplicative inverse? We'll call this X inverse as a multiplicative inverse. Will there a multiplicative inverse exist? As the product of element from this set and the product of a multiplicative inverse will give me the multiplicative identity 1. Okay, and the answer is no. For example, let's consider the integer 2. 2 multiplied with 1 by 2 gives me 1. This is assuming that I am following the conventional definition of the product. Okay, 2 multiplied with 1 by 2 will be 1. But is 1 by 2 an integer? It is not. So 1 by 2 does not belong to Z. Okay, so what we have said as a fourth property listed here, that the unique inverse element should also belong to the same set. So in this case, the integer 2 belongs to the set Z, but 1 by 2 is not an integer and it hence does not belong to the set Z. Okay, so you cannot find a multiplicative inverse for, there is at least one element for which you can show that there is no multiplicative inverse. In fact, you look for 3, 4, 5, 6, or minus 1, minus 2, sorry, not minus 1. If you look for minus 2, minus 3, minus 4, minus 5, and so on, for all these, you do not have a multiplicative inverse that exists in the set Z itself. Okay, so Z here is not a field. This is not a field when we use the conventional definition of addition and product operation. Okay. Please note that these are just two operators that have been defined. Okay. With respect to one operator, you have a set of properties. With respect to another operator, you have a set of properties. And with respect to both the operators combined, you have a property. This will be distributed. Okay. Each of them needs to have certain things satisfied. Okay. Here I am considering the plus sign to be doing the conventional addition operation and the dot sign to be doing the conventional multiplication operation. Okay. So under those conventional addition and multiplication operations, set of integer Z is not a field. Okay. I request you to also find out or try finding out examples where a set under two binary operators can be qualified as a field. Okay, that's it.